All right, ready to start. Mm-hmm. Day 6 starting soon. 20 seconds left. All right. Mm-hmm. Map. Interesting. Yeah, all right. Map. Okay. Let's see. Let's see what the characters we get. We get dot, hash, and I guess the starting position. Index in. There you go. Okay. So that'll be our map. Let's see what we need to do with it. Still have to be careful of time paradoxes, so it will be important to avoid anyone from 1518 while the historians search for the chief. Oh, do we go back in time? We have direct access to history. Okay. Historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. Okay. Maybe you can work out where the guard will go ahead of time so that the historians can search safely. Okay. So there's a map. The map shows the current position of the guard. He is facing up. Any obstructions are shown as star. Okay, lab guards in 1518 follow a very strict patrol protocol which involve repeatedly following these steps. If there is something directly in front of you, turn right. Otherwise, go forward. Okay? So he goes straight, right? Then he turns 90 degrees to the right. There's an obstacle in front of the car. She turns right before continuing again. Boom, boom, boom. Okay. And then we get here. 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 And then we leave the map right here, right? We'll just scroll through. Yeah. And we leave the map. Yeah. I just count. Okay. All right. I wonder what part 2 will be. Anyway, how shall we do this? Yeah, just recursive search, I guess. Okay. Honestly, usually things like this I will solve with complex numbers, maybe. In this case, maybe not. Let's see. So, Let me just check something. At what's the index? Where it's 264, okay. So at 6.5, I'll put a 3. Of course not. That's not how it works. Okay. So I want 5.5. No. It's 4.5.4. Okay, so the going up is so the direction is 0, 1. No, sorry. Subtracting 1, 0. And if you turn right, you will go 1, 0, 1. And if you turn right, it's 1, 0. And the next direction will be 0, -1. Okay. Okay. So start position. Well, let's do it like this, right? So we take a start. And yeah, 6.4. Okay. Yeah. All right. 6.4 is where we start. We try to look at the map at that position. Yeah, it's 2. If it's equal to 1, then we need to turn right. Alpha will be the which direction, right? Which direction? Then we call self with a alpha plus 1. Yeah, we just call the same. Yeah, so if we hit a wall, then if next move dir at alpha is next move is a wall, then we turn 90 degrees, right? Move on to the next direction and call recurse. Okay. Yeah. Otherwise, we call recursively alpha plus whatever the direction of us is. Let me check what this does. No. And of course, we need to do for module. Boolean singleton required. Okay, alpha direction w plus, no, hold up, w plus 5.4, and then we'll look up m. That's what we want. And to the alpha, and I want to print. Eventually, we'll hit the but because alpha. Yeah, okay. The way. There you go. Okay. Yeah, so we get a bunch of moves until we get index error. I can handle index error, or I can just in here look for index error. Just catch the error. I think it's like this, and I think it's like this. Done. Can we say done? Okay, I'm done. All right. We need to accumulate how many steps. I guess we could just return 0. Otherwise, 1 plus 44. Is that right? 41. Missing 1. Okay. Well, but this, every time we move, we update equal to 3, right? Does that work? Okay, and then we'll show the map. Okay, so far so good. This is not that hard. The 3 will be x's, I think they use. Right, so how come we have an extra one? Because there are repeated ones. Because there are repeated ones, right? We cross paths. So there's some duplication. Okay, so can't just do +1. We need to accumulate into some sort of set of things. Or, honestly, we could just update the map, right? And then count how many hexes there are. And we call 3, I think. Sum of okay, now we're off by 1. What are we missing? Last one is missing. Okay, just switch this around. Yep, and yeah, so what was missing was the last one, right? Because before I was updating the current position. Yeah, anyway. Okay, just kind of there. Yeah, some 131. Wait, 3 equal 41. Don't need to display here anything. Apparently display something, doesn't really matter. All right, because this keeps returning 0 at the end. Yeah. Let's run it for production, for real input. Okay, all right. I imagine part 2 is more interesting. Okay, from the safety of the supply closet, you time travel through the last few months and record the nightly status of the guards. Labs guards post on the walls of the closet. Okay, all right. Fortunately, they're pretty sure that adding a single new obstruction won't cause a time paradox. Oh, actually, hold up. Returning after what seems like only a few seconds, they explain that the guards' patrol area is simply too large for them to safely search without getting caught. Fortunately, they're pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place a new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab search safe to search. Ooh, okay. To have the lowest chance of creating a time paradox, the historian would like to know all of the possible positions for such an obstruction. The new obstruction can be placed at the guard's starting position, obviously. We want to know all the possible positions. So here we can do 6 different positions, right? All right. So we need to get to a situation where we're in a loop. And to check that we're in a loop, we need to check that we've been here before. We've been here before. So the best way sounds like it would be to change actually our original program. Is there anything else that I'm missing here? So we go up and we change the abstraction here. I wonder if there's a yeah. Can we what can we do? So we can either as we go through because it might be okay, so we can check for every position, right? Obviously, run this algorithm for every, would just permutate every possible position, adding a boulder or whatever it's called, the obstruction in each one, and then just run the algorithm and check if it goes in loop or not. So that's one way. Another way is as we search, we can split up searches, right? So like when we get to a situation, like if there's a boulder, like continues normal, but if there is no boulder, switch, imagine there was one in front of you. Imagine there was one. That will get real tricky real fast. How big is production input? Shape of M. 130 by 130? It's not that big. We could do a search. I wonder what if, so 130 by 130, right? 130 by 130. I mean, it's less, right? But so 10,000. Let's run our algorithm 10,000 times and see what happens. So I will do this. I will well, what's the best way to do this? There's a function, just call it whatever, nothing function, right? And it just doesn't do anything except that this function, right? So that does nothing, right? But instead we'll call it, well, let's call it just 10 times. What? Just forget about it. Come on. Single. Okay. So I'm guessing calling it twice is too much. I don't like this. Anyway, so what I'm trying to do is just run the algorithm down the path 10,000 times, just to see if this will work. If this is fast enough. For some reason, it's not working for me. Let me comment this out. I don't think I need this. I don't know if that's a problem. Okay. What? Is it already? That's already slow. Why? 3 times? 4 times? Okay, 4 times already is 1 second for us to run this. Yeah, so 10,000 times is not very usable. You need to be smart about it. I mean, realistically, how many? So we have an M, right? Flatten key. Well, to actually do a key. We've split up So we have 16,000 empty spots, right? 800 boulders. Actually run this code, right? To do, yeah, 800 boulders, and oh, I know why. I know what happened there. I messed up. Hold up. But anyway, what I wanted to see is how many positions we actually look at. So 4,000, right? Or 5,000, right? So 5,000 positions. If we but it's so fast, 100 milliseconds at most. How was I getting a second? Why is it so slow? 400. Just running it another time was 400. Why? Why? I don't understand why. If I call why it's so slow is my question. Why is it so slow? Running it once even. No, that's because this function is weird, right? It's because this function just doing the same thing is slow. It's just fast, right? Yeah, no, it's fast. Come on. Well, 100 times is 1 second. 1,000 times will be 10 seconds, I guess. Right, and 10,000 times will be 100 seconds. um, hmm. Yeah, running it 100 times, 1,000 times will be 10 seconds, right? All right. Yeah, so that's not very tangible because again, when we run it and look at the result, we haven't visited most of the spots we haven't been visited, right? So it doesn't make sense to go see them. So as we traverse, there's only like about at most 4,000, 5,000 positions where we would check, right? Because yeah. Okay. Um, yeah. So we don't. It doesn't make sense to just run it for each input. It does, but we don't need to run it for each input, right? We just need to run it for all of the, so we know the path, that we take. We record all the positions where we can even consider putting something, right? So it's basically everywhere as we walk, everywhere where we're in front of something, where we can move there, right? Which means anywhere where we have moved. All right. Okay, let me switch to this one. So here's what I'm thinking. We run the algorithm once, right? When we run it, we figure out all of the positions where we've been, yeah, and try to put in a boulder in there and just rerun again. So just run it 5,000 times, right? It's wasteful, right? Because let's say, I don't know, what's a good one here? This one, right? So for example, here, we started here, we went up, right, down, left, right, up, down, left, up, right. So we spent all the time, and then it's here where we just put the boulder. So we took all that path, all of that, thing, all of that compute time to compute this, and we can't just be like, okay, well, rerun this and see if we put a boulder here, what happens? Well, we're just gonna run the same thing again, and eventually, no. See, that's not good. All right. First thing first, I need to make some changes to my algorithm here. So let me get rid of this. Let me get rid of this. So we're definitely not changing map because that's silly. Here we're gonna return 0 because that will be that. And what else? Direction. Just call it with 0. Honestly, who cares? Yeah. Direction and when. So right now, what happens? Yeah, just return 0 eventually. When we call. Right, I wanted to see if there's a loop, right? Because right now, if I put a boulder in one of those 6 positions, it will break. So one other thing that I want to put in here is the map, right? So the map will be the omega omega. But what's your problem? It's a function that value error. Where's the value error? Okay. Right, because can't just put it here. It has to be, we have to start with alpha alpha. Yeah, okay. Okay, that's fine. Alpha alpha will be our map, okay. And I'm gonna switch it. So this way I can pass it a different map and then it will just work. The map I'll pass it will be like, you know, the boulder is here. Instead of the direction, I want to switch this to something else, and the something else will be let me just actually get rid of this alpha alpha business. We don't need it right now. Yeah, so instead of the direction being, instead of alpha being the direction, we want this to be where we've been so far. So where we've been so far is going to be nothing, empty list, right? Oops, come on. Oops. Where is it? There you go. Empty list, we start with empty list, right? And every time we've been somewhere, we technically it's going to be this, and I want the direction to be there as well. So we want to detect loops. So this will be this added with a 0. Let me just see what it returns. Yeah, no, that's not good. Latent and close. There you go. Okay. And then if I check if, what if I take 2 of that? There you go. So something like that, right? And then I will check if if 064 exists. Oops, exists there. Not like that, like this. Yeah, 064 exists there. What about 063? Doesn't exist. Yeah, so this is checking if we've been someplace. Maybe optimize something here, but no. This being direction. Oh, yeah, we need the direction to be there as well, right? Because if we're just doing crisscross, that doesn't mean that we've been there. That's not a loop. That just means we are yeah, going through the just crisscrossing. It has to be we have been there in the same, we're facing the same direction as well. Yeah, okay. So so if the direction and the position that we're at is okay, actually, so the current position will be this, right? We'll keep this as an empty list, honestly, right? So alpha omega is this. We check if it's a loop, blah blah. Okay, then when we, how do we check? We don't have alpha anymore. We want to check if there's a boulder in front of us. I'm just trying to rewrite part 1 for now, right? Just to make it a bit more generic, and then we'll change it to be like fancier. Right. Right, okay. So not actually doing any fork. We're gonna fork. We're gonna fork at every point. We're not doing any forking right now. So let's just make sure that the new situation here works. So this is our current position, right? So we want to get direction. Direction is going to be current position, right? I don't need this anymore. Well, I'll print this, right? Display. Yeah, nice. Okay. First, it's gonna be 0, of course. Yes. Direction at that position, -1, 0. Then we added well, this is where we added to 1 drop W, right? But oops. Whoa, right. Because this returns, I don't like this at all. Right. So these are different things. Crap. I mean, technically it's this, right? Or we can take from, would that work? Yeah, okay. And then add together, that will be the new position. So that's this whole thing. And we take that from map rank error. My God, this is, I think there's an easier way. No, first W, I like this, and we want to keep it as a thing. And in case, right, and add 5, 4, okay, so we don't need these brackets anymore, okay, and then at map position 5, 4, 0, okay, and we check if it's 0. If it's 0, then if it's 1, then what do? Then calling visited is still the same. No, visited is now direction. Well, if we didn't change anything, we're just changing the direct. Well, yeah, the direction. Do we want to record the position? We do want to record it, right? So in this situation, yeah, so if this is true, we don't know yet to do, right? What do we want to churn, right? So we're gonna call this position is going to be the same except position will be the same, except we want to change the direction. Now, technically, the direction needs to be changed, right? So at omega, right? At 0, we want to update it and make it be I think the function way, right, would be 1 plus. No, it's a Boolean matrix 7-4. What? Zero 6 4 1 7 4. What? Does that work? Okay. So that work? Yeah. Okay. So if I add 2, 3, 4. Yeah. Cool. All right. So add one more to the 0th position, right? So that's our new direction, and visit is still the same. So that's that. We can do one minor thing here to update what we've seen. So this is, again, this is the wall, right? If we hit the wall, then we call, we update our position, we increment the direction, sorry. The direction gets updated, incremented by 1. Then we call the visited path to be stays the same. Technically we can make an optimization, but I don't think it matters here that much. At most it will be, no, we can optimize it later. Right, but now we need to do the normal path. The normal path is there's no wall. What do we do? Well, technically we can take the alpha, direction first. Direction, what are we trying here? Oh, we're updating the position, right? Yeah, we're updating the position. So one thing we do is we update the position, and direction plus first of 1 drop W, right? That's what we're doing. Just actually move there. 5 4, okay. And 5 4. To move there, and we need to update also visited path. 5 4. Right, and the direction will be, we're going to keep the direction. The direction will be the first of omega. Come on, what? Wait. Yeah, 0 5 4 technically is, yeah, this is so ugly. Let me check again. So 1 drop W. What if we do this? First of W, this gives us direction. Direction gives us the direction vector. We take it out, or even yeah, take from 1 0, right? That's the same thing. No, I don't like this. I prefer just simpler. Then we add a 0 to it, right? And add to our current position. Yeah, there you go. We'll kind of make this extra vector, but it's only 3 elements. It's fine. So that's our new position. Yay. Then we call ourselves, but with omega being updated with W, right? Something like that. That'll work. Right, we just see in the beginning. So in the beginning, our visited vector is empty, then it's 0, 6, 4, 0, 5, 6, 4, 0, 5, 4, etc. Yeah. Okay, okay. All right, all right, all right. Yeah, that's fine. Yeah, and it just keeps going. Sounds like it works, right? Right, we don't need this anymore. This is old code. So at the end, we will have, once we hit the loop, we get what? We get, take alpha, convert it to an array, one drop. No, we want to like drop the first. Is there like drop column? Remove leading black columns, drop ith column from the matrix. No. Wait. 0. Oops. What's going on here? How does this work? It doesn't do anything. Okay, so one drop each of omega, right? And then unique it, and then count 40, right? So we're missing something. Add this position on the map, set 3, I don't know, that work? Yeah, we're missing the last one, yeah, of course. +1, right, honestly. Because we're in a position, yeah. It's fine. So that's how many times we've gone through the loop. Yeah, anyway. Okay, but I just still solving the first part. Now, how do we solve it? Where? How do we solve the second part? So my thinking is this, every time here, instead of just going through, we try putting a boulder right in front of us, right? We know here that we haven't visited wall, we haven't checked that yet. Let me put a boulder somewhere. Where's a good boulder? Boulder, what's the easiest one? Is at this location. It's 5, I don't know. 4, 4, put a 9 there. Not even close. 6, yeah, 3, yeah, okay. 6, 3, we'll put the boulder like this, right next to the entrance, yeah. And if we run it, anyway, yeah, so we're going to try with this map, right? And as I passed it before, as I mentioned before, I'm just gonna put it in here as a alpha. So anytime we touch a map, that will be alpha instead. So now it will just loop infinitely because eventually it will just come back, right? We just need to detect the loop. Value error. It's a problem. I don't know. Where's the yeah, it just keeps on looping, yeah. So we just need to check if length of alpha equal, I just check 4, right? We can probably check this is 3, another 3, and 4 and 4. So what is 3 plus 3 plus 4 plus 4 plus 4 corners? 18, right? 18. If it's 18, just give me back alpha. Yeah, all right. Let's take a look at it. 6, 5 and 6, 4. So we started at 6, 5, right? And technically here we would check. I already forgot what's our starting position was. 6, 4. Okay. Yeah, 6, 4 makes sense. 0, 6, 4, and we want to check if we are in 0, 6, 4, if we've been there, and we will have been there. So we make one more move here. It's a boulder, so we turn. And then we do one more move, and then we're turned and we're facing up, right? Facing up. Yeah, I don't know how this is actually, because we checked. Okay, it works. I don't know. I don't actually understand how 064 made it to the list. Oh, right, because we moved there. Okay. And now we can check if omega, which is 5,4, it will have been in alpha. That's 064. It's 054 is there. Oops, exactly there. Resize accidentally. Okay, so let's check if omega belongs. No. Enclosed. Yeah, enclosed. So if closed in A. So if enclosed omega exists in A alpha, then we return 0. Good. Okay. Um, yeah. All right. Let's also, yes, in our case, it wouldn't be, why would it be 0? Ah, right, because I did this thingamajig. Okay. Okay. We'll just apply map. It will be 41. So every time we run, what I want to also add is, we want to run this obviously, but we also want to run the same thing and saying, hey, imagine there was a boulder. Imagine there was a boulder. So we know there's no boulder in front of us. Imagine there was one, right? We know we can move there, technically. We know it's not outside because it would have been hit by this situation. So imagine there's a boulder there. So we call ourselves with visited same. Well, I guess no, we need to check. Yeah, we need to check if there's a boulder. So we go there. We just go there and just be like, hey, you check. We want to trigger this path, yeah, but in a separate function. So same situation, right? We call ourselves, but the map will be can we hack it somehow? No, we need to make sure that the boulder exists on the map. I'm just thinking, like, can we hack in a way where we're like, we've been there already somehow? But no, we need to put a boulder in because that boulder can be hit from another direction, right? If we put the boulder in, he can come back and do a loop around and hit it from a different side of the map, right? So we actually want to put the map in of, so we're currently I'll call it N because we keep combining it, right? So so drop one from the map and close it, add the direction, so that will be the new, right? And this is where we put the boulder, and at that new location or obstacle, we'll call it obstacle, right? Obstacle goes here, and we call ourselves as is, right? Now I will also have this thing, I will change it to 1. The reason is if we've already put a boulder on the map, we don't want to do it again, right? So we have this binary thing that says, hey, we haven't put any boulders, right? As soon as we put a boulder in, we say, okay, we've put a boulder in, don't try to put any more boulders, right? So we'll have to have a loop where we say omega is 0, then maybe just do this thing as before. Sorry, if it's 1, no, sorry, if it's 1, if it's already 1, we've already put something on, then just call as is, just keep moving, right? Just keep moving until you're done, right? Otherwise, we we know that there is no boulder in front, and we know that we haven't tried to put a boulder in. So try to put a boulder in, run it. This will give us the result, okay, return value. Hopefully, right? So we call ourselves, we didn't change anything here. Didn't change anything here. I'm also worried that, like, as we go through, we might put a boulder somewhere where we've been, but that might be some duplicates. Yeah, there might be some duplicates. That's okay. We'll figure it out. We'll figure it out. So that's a return value. And we also want to run the normal path, right? And we just add whatever this guy returns to the result. That's right. Okay, just something. Okay, what are we getting here? Okay, there's a bunch of numbers. I don't understand why there'd be numbers here. Did something. So this should return either. The only way this function returns something is at the end, number of repeats, right? Alpha number of, we drop one from each, we've hit the infinite loop, and sorry, we've left the map. So we make a unique count. By the way, that was really slow, so either this algorithm is not fast enough or something else. Number unique plus one. Otherwise, we so that should be a single number. If we've hit, now this doesn't. I mean, the return out. Another one is here 0. If we've hit an infinite loop, we'll return 0. So that's a single value of 0. This is calling somebody else. This is calling somebody else. Let's try. Okay, if R is true, boulder at next, no, obstacle, and then some of that in the result. Oh, why are you printing so much? Boulder at 5.4. Yeah, that's fine if we update the original map. Fine. Zero, 6.4. I don't understand how this is coming about. So try to put a boulder right away, right? 5.4. We can't put a boulder at 5.4, so that's not anything. Sorry, this is infinite, right? This is infinite. Yeah, if 5.4 we're gonna have infinite loop, but we're gonna disregard that one. That's fine. because we're trying to put a boulder where we started. That's not good. Why are we? I don't understand how this works. Yeah, I don't understand why. Why I return a bunch of different things. Boulder at the position 5-4. So we try 5-4. Now we get infinite loop and some other stuff. Here's what I understand. Like, where is it coming from? So we call this guy, right? Just display what the hell is this? This will always just return infinite loop, inf, right? That's it. It just returns inf. So we call this method, right? This method will do some stuff, and eventually it will either hit this one, where we take the omega first direction first, 0 plus omega, infinite loop into the self plus abyss. Why is there 064 added at the end? I don't understand this. It's literally the same code. We call this omega recursively w plus 0 direction blah blah blah. Let me try calling it. Okay, I know. We'll call it with 1 already, right? And we'll say, hey, yeah, nothing changes. Okay, good. Okay, good. So first we have nothing, 064, 064, 054, 064, 054, 044. Right, and just keep on moving. Okay, yeah. This is properly, that's proper, okay. And at the end, what does it return? It returns 41, makes sense. Now, if I run map with at 6-4 apparently, right? We'll put a 1 in there. I'll put in the bracket thing. 23, right? 064, 064, 054. Why would you return 23? Why 23? Right, I know why 23. I know why 23 because we put the map, we put the boulder right here, and then we don't know what's happening here. This is just silly. No, that one's not good. That one's not good. But let's put a boulder at not 0, 0, 1, 2, 3, 4, 0, 6, 3, right? What happens here? Infinite, just infinite, right? That's it. So that's exactly what we did. We have the same alpha, didn't change it. Same omega, didn't change it. Omega is 1, just like we called it. And the map at obstacle is 1. There. So when we run this function with, I don't know. Okay, so when we run at 6.3, 6.3 is what we want. Map 0. Bold. I can't search them here. 5.4 boulder. Okay. Just copy this somewhere else. Six, 3. Wrap. Yeah. Okay, if we put a boulder at 6.3, why the hell is it returning this garbage? Why are you returning other stuff? Why are you returning your path? That makes no sense. Why are you returning 364? That makes no sense. And inf makes sense to be returned because we hit an infinite loop. Good. All of these are infinite loops. No way. No way these are all infinite loops. That doesn't make sense. All of these are infinite? No. No, something's wrong. Put a boulder here, here, here. There's no way it's an infinite loop. Only at 6.3. Where is it? Right here, 6.3. What's so special about this is because we... Okay, all right, so let's imagine we put a boulder at 3.4, right? So 0, 1, 2, 0, 1, 2, 3. And from the bottom, 0, 1, 2, 3. We put a boulder right here, right? 0, 1, 0, 1, 2, 3, 4. So we put a boulder right here. What happens? What happens? 2 to the right. We put a boulder. Where's the map? We put a boulder right here. Ah, stupid scroll. Okay. We go up, right, down, left, up, down. We still leave. We still leave. So it's not infinite. We'll leave the map. Is it because okay, didn't get far. I solved part 1, but part 2 is the harder one. We were trying to use the forking method, so this is where we say fork with boulder in front of us. I'll try to fix it during the day today. Otherwise, yeah, gotta move on with my day. Thanks everyone for joining. 2 people here. Oh, how are you going? Mine just finished. Good, man. When did you say this? Did I miss it? Oh, this was a while ago. Why am I missing chats all the time? How do you determine if you're in a loop? How do you determine? So I have a code right. Where is it? So I keep track of where I've been, basically, right? So I start with an empty vector, visited vector, and then eventually, if I've been Where do I check that? If the current position is with direction, right? Is in the I've been there vector, then I've been here before, and I just return infinite loop, right? Just so I can see that inf, right? I plan to return something else, but just inf for now. But for some reason, I think I have like one extra variable somewhere being added or something like that. It doesn't. Oh, doy, I'm dumb because I need to call this. This is what I need to call, right? Because I'm changing alpha, alpha, and omega, omega. So I need to change. I need to call it. Okay. So now, this one's boring. It only has 6, 7, 22, 99, 20, 10. Okay, I'm looking for an infinite at 6, 3, I believe. Okay, so we're coming back around. There you go. We hit a 6, 3. That's an infinite loop. Yay. Then there's a bunch of other stuff. There's another infinite. Okay. Yo. Okay. Was just checking if you were tracking direction 2. At first I found way too many fake loops because I was just checking the, oh yeah, see, I figured that like just because they crisscrossed that, I mean, even on the map that we have here, like they crisscross, where did they have? Yeah, just the first one, right? They crisscross right here, but that's not a loop, right? That's not a loop right here, where the plus is. They just have been crossing the paths. Okay. Yeah, okay, I guess 86 loops on that sample instead of 6. Yeah, makes sense. A little surprised that I didn't. No, it makes sense. Yeah, makes sense. Yeah. All right, so then instead of inf, I will return 0. Instead of this, I will return whatever the result was, plus the result will just be an integer, plus whatever the main loop will return. Okay, and then I will just count number of zeros, and hopefully they are 6. Yo, okay. So data, let me just get the data, right? So this is data. So first part is resolve, give me the last one, which will be the main loop, and sum of zeros in the D. Okay, so we got that. Let's see if it runs for real input. It's slow. So if I remember correctly, there were 4,000 boulders. About 4,000 boulder positions, 5,000 boulder positions that we need to evaluate. Yeah, bag of potatoes if you're still here. So the original plan that I had, my first work in part 2 took 2 minutes. It was testing an obstacle at almost every possible location on the map. When I changed it to test only every location in the original map, it still took 30 seconds. I see. Okay. But 2 minutes still, it was, I that's the approach I took at first. Well, I didn't take an approach. I just ran my part 1 10,000 times, right? Because that's how many positions there are on the map. It's like 16,000. So I tried that at first, and I saw that it was way too slow. So I guess it wasn't that slow. It was like 100 seconds. I didn't want 100 seconds is not even that much. Yeah. So technically could try every possible position, but guess instead of forking, the reason I did the forking way is because I figured it would be faster this way, because if you just like the other approach I wanted to take was just do a walk first, figure out where like normal path is, original path, yeah, and then for every position on a map on that path, put a boulder and just rerun it. So it'll be about 5,000 times, and yeah, K. My K is really fast. I don't know about this solution, this problem, but K is surprisingly fast, I find, if it's written properly. All right, it's taking some time. It might take more than 2 minutes. It's not very optimal, but I'm gonna go. Actually, I need to run. But thank you so much for joining again, and have a good Friday. Have a good Friday. Yeah, at some point it will complete, and I will post a solution. All right, bye all. Bye.